So last time we started talking about errors, right? What are our sources of errors? What are some things that we can try to do or hope to have in our problem and our method that will keep our errors from just completely blowing up on us? So last time I think we said, well, we should be trying to solve a well-posed problem to begin with, otherwise we're kind of screwed from the start. And then ideally it's a well-conditioned problem, right? So that, if we end up making solving a problem that's very, very, very close by to the real problem, hopefully we're going to get a solution that's actually also close to the solution that we want. So there's a few other things that we can be concerned about. One is that we want to try to avoid losing too many significant figures along the way. So let's try to avoid processes that lose significant figures. Right, so we're working with a computer that can only store finitely many digits. So automatically from the start, we don't have infinite precision. But now we're doing computations along the way. Each time we do a computation, we're stuck rounding to 15 decimal places or whatever, right? And every time we round like this, we lose a little bit. Now, some processes are kind of stable in this way, that each time we do this process, we lose a tiny bit. Some processes are kind of less stable, and every time we do this process, it can actually lose quite a lot of error, much more than you would expect. So let's just think about some of these examples. So let's just say, okay, I have the quantity that I'm working with. So A is the quantity that I'd like to work with, except I stick it in the computer and I round to however many significant figures. So what I've actually got is an approximation, A tilde, and there's some error, and then I do the same thing with some other quantity. Okay, and now I want to say add A and B together. Okay, so the absolute error in A tilde plus B tilde is what? We want to look at A tilde plus B tilde, the thing we actually compute when we do the addition minus the thing that we would like to be computing. Okay, so the error we end up with is going to look like basically the error in A plus the error in B. And that's probably reasonable, right? We can't expect the error to stay the same. Every time we do something in a round, we're going to lose something. But this is pretty good. Maybe the error in A was, on the order of 10 to the minus 15. Now when we do an addition, the error is on the order of 2 times 10 to the minus 15. And if we added something else, okay, now the error is on the order of 3 times 10 to the minus 15. It's going up kind of slowly. So that's good. And the relative error, right, is just going to be the error divided by the actual quantity we're interested in. So delta A plus delta B over A plus B. Okay, so addition maybe makes sense. Things hopefully do what you expect. Let's start stringing some processes together now. Yeah?
So the first one I understand is we can theoretically know delta A and delta B, but we don't know A and B a priori, so how would we calculate relative error?
Okay, so you're asking, so maybe we know delta A and delta B, but we don't know the actual sum, so how do we calculate the relative error? What we're typically going to have is not the exact error, but we have bounds on the error. So we might say the error in this was delta A, the error in this was delta B, or bounded by delta A, right? Maybe I know that when I'm rounding, my error is going to be on the order of, at most, 10 to the minus 15. Maybe this, maybe this has a nice finite precision representation, like 0.5. Okay, my error is 0, but my error that's 0 is still certainly less than 10 to the minus 15. So you could think of these as actually error bounds and not things that we know exactly.
Okay, so we would never calculate the relative error.
Exactly. We would never exactly calculate. If you can calculate the exact error, which, in test problems you'll do that. You'll say, here's a problem where I know an exact solution. and I can check to make sure my algorithm is doing the right thing. But in real life, we have bounds on this. We can say, I know the error is less than this, and I know the error is less than this. And I have an estimate of what A plus B is. Right, and with a bound on the error, I know kind of how accurate, what's the worst case A plus B is, what's the smallest or biggest this could be. But yeah, in real life, if you know the actual error, then you know the actual solution. So let's try stringing some processes together. So let's say we want to solve a quadratic equation. Okay, and for the purpose of this example, I'm going to assume that we are able to work with 5 significant figures. Okay, so I want to solve the quadratic equation. We have a quadratic formula, but anytime along the way, I can only store 5 digits at a time. Okay, so I add 2 numbers together, I have to round to 5 digits. I multiply 2 numbers together, I've got to round to 5 digits after every computation. So I say, okay, let's find one of the roots of this. Well, one of the roots is this. Let's take the one with the plus. Okay, and I compute this again using 5-digit arithmetic. So I multiply B times B, and I take that result, and I round to 5 digits. I multiply A times C, I round that to 5 digits, right? I do the subtraction, I round to 5 digits. Every time I do something, I round to 5 digits. Okay, and if I do that, at the end of the day, I'm going to get to 5 digits, something like this. Okay, so this was with 5-digit arithmetic. Okay, now here's an example of a simple test problem where I can, check what the method would do, check what 5-digit arithmetic would do here, and okay, this is something that I could actually easily solve to much higher precision. So we could do that and say, well, how does this compare with the true answer? Well, the true answer is going to be x1 equals minus 0.010910. Right, so I'm doing 5-digit arithmetic. I'm storing 5 digits, and I've only done a small number of operations here. It's not a complicated formula. But what have I got? At best, I've got 1 digit of accuracy. Right, if you decide to round this up, I don't even have that. So it's not very, on a quadratic equation is the simplest thing you're ever going to have to solve in real life, just about, right? And we can't even do that well here. So what's going on? Do you have any guesses as to what could be the biggest source of the error here? What's really going wrong in all of this?
Cancellation on the numerator.
Some cancellation in the numerator. Yeah, so let's look at this. Let's go back to here, the relative error. I wrote down not just the absolute error, but the relative error, and this is what's important. So delta A plus delta B, so if delta A and delta B are both small, this numerator is small, that's great. What could go wrong in the relative error here? Right? Numerator is always small. What could cause this to nevertheless be large? A small denominator. So if A happened to be equal to minus B, or if A happened to be approximately equal to minus B, right? It doesn't matter that this numerator is small. This denominator is really small, and my relative error is going to blow up on me. And that is essentially what's going to happen here. So we can dig in here a little bit and see, where's my numbers? I look at my b squared here. So that's this guy squared. That's a relatively big number. And then I look at my for AC here. A is 1. C is, a little bigger than 1. So this is pretty small compared to this. So this number in here is going to be pretty close to b squared, right? Once we round to 5 significant figures, it's going to be pretty much b squared. So the square root of this is going to be really close to b. So what am I doing here? I'm doing minus b plus something that's really close to b. And I've gotten myself into this situation where my relative error is going to blow up on me. And relative error is a big deal when I only have 5 5 digits that I can store here. So here the biggest source of error is really subtraction of nearly equal numbers. Subtraction of nearly equal numbers is always a bad thing. It always has the potential to lead to this kind of problem. Oh, now this wouldn't have been a problem if I was looking for the other root of this quadratic equation, right? If I looked for the minus here, then effectively I'd be doing minus b and then minus something approximately b again. Basically addition of nearly equal numbers. That's no problem, right? That won't blow up my relative error. But the subtraction is a problem, so what can we do to get around this? I still want to solve this quadratic equation, and I still only have 5 digits I can work with.
Rationalize.
I can rationalize, exactly. So you can be clever, right? You can be aware that this kind of thing is bad. This kind of thing has the potential to lead to very large relative errors. And then you look through your computations and say, is there anywhere in my computations where this is likely to occur? And secondly, can I now try to rewrite the computation in a way that gets around that? So I'm still computing the exact same number, but using a slightly different process, or multiplying and dividing in slightly different order to try to prevent this relative error from blowing up. So here, indeed, we can try to be clever and just rewrite the formula a little bit. So rewrite to avoid these bad operations. Okay, so say I multiply both the numerator and denominator by b plus the square root, denominator by b plus the square root. Okay, I get some calculation on top. So I'm going to get minus b squared plus b squared minus 4ac on top. In the denominator, I have to multiply by the same thing. So b plus root b squared minus 4ac. Okay, which simplifies. Okay, it's exactly the same quantity, right? I haven't changed the number. All I've done is taken this and multiplied by 1, or I've written 1 in a clever way. And now what's happened? Now in the denominator, I have b plus something that's really close to b. And that's no big deal as far as the relative error is concerned. So this is something, I didn't write down what the actual number is. You can check if you want with the 5-digit arithmetic. But this is something that will give you a much better result for this root. Now, if I was looking for the other root with the minus sign, I would want to use this formula, right? This formula is the one that involves adding nearly equal numbers if I'm doing the minus root. If I'm doing the plus root, this formula is the one that involves adding nearly equal numbers. So you might need a different approach for both roots, certainly. Any questions on that? Make sense? Okay, you get a chance to practice this a bit in your homework. With other operations, we might want to know, maybe we're doing some kind of nonlinear operation, and we want to know how does the error propagate through a function f. Right, so I want to compute f of a, whatever f is. What I actually compute is f of a plus delta a. And again, I want to look at the error in that. Okay, and how can I estimate the error of that? It looks like a derivative, exactly. So this is going to look approximately like f prime of a, or equivalently f prime of equal to f prime evaluated somewhere in the middle, times delta a. right? So as long as the function you have here is kind of differentiable and the derivative stays under control, sticking your approximation into a function is not going to kill your error, right? It's going to multiply it by whatever the derivative is at worst. Of course, if you stuck this into a discontinuous function, that would be a whole different ballgame because, you might say the thing you want is here, and f is down here, and then you move it a little bit. Oh, the function is discontinuous. It could jump. So if you got a discontinuous function, you should be worried. But if you have a nice continuously differentiable function, you're generally in good shape. Okay, so think about how we're losing significant figures. Unfortunately, in real life, our computers can work with more than 5 digits, right? We also, okay, I have a function here. I have to be able to approximate this function somehow. Okay, so I can do simple operations sort of exactly and round. I can add, I could subtract, I could multiply and divide, but maybe you want something more complicated. You want some nonlinear function, and we need to somehow approximate it. So for example, you need to know cosine of 0.1, let's say. So what happens? You plug this into your calculator or your computer or whatever. Your calculator is not storing the infinitely many possible different values of cosine function that it could take on, right? So what does it do? It has to do something to come up with a good enough guess at this. Maybe your calculator displays 8 digits or something. It needs to come up with a way of giving you something that's accurate to those 8 digits. So what's an easy way to estimate the cosine function? Taylor expansion, yeah. So let's do a truncated Taylor expansion. And what we're worried about is not just that we get a number out, but how accurate is that number? Is my calculator really giving me 8 digits correct or not? So we need to know not just how to do a Taylor approximation, but we need to know how to bound the error. We need to know Taylor's remainders theorem. So here we're concerned with the accuracy. Okay, so here's kind of a formal definition of how we talk about accuracy and rates of convergence. So let's suppose that we have some sequence that converges to a number. So for example, this might be the nth order Taylor approximation to cosine 0.1. So I use n terms in my Taylor series, plug in 0.1, see what I get. And as I take n bigger and bigger, I should get closer and closer to the real value. Okay, so we suppose this is true, and we suppose that there exists some constant k such that alpha n minus alpha, so such that the error is bounded by k over n to the p, as long as n is large enough. Okay, then we're going to say that alpha n converges with the rate big O. Have you seen big O notation before? Most of you? Big O of 1 over n to the p. Right, so if I look at the picture, say this is my error, and I get different approximations for different values of n, and we hopefully have the error going eventually to 0. And the arrow might go up at first, but eventually it should go down. Okay, now I say, can I draw a curve like 1 over n or 1 over n squared, such that eventually all these data points are going to lie below my curve? So maybe I find that I can draw a curve like 1 over n squared. And some of these errors are above my 1 over n squared curve, but eventually, when n is large enough, they all sit below here. If this curve is 1 over n squared, then we're going to say that the error is big O of 1 over n squared. Even if this is 2 over n squared. The constant is not a big deal. It's really the over n squared part that tells us how quickly is this error going to 0. Right? And the faster the error goes to 0, the fewer terms we would hopefully need to get an accurate result. Okay, so if we go back to our cosine example, we know that cosine of 1 over n converges to 1. Okay, and if we decide to do an approximation of this, we're going to get what? Cosine of x equals 1 plus. Okay, the linear term is 0 times x. So, right, the first order approximation means I have the linear term in here, which is 0 in this case, plus some error. Okay, and we know from Taylor's remainders theorem that the error basically looks like the next term in the Taylor series. So this is cosine double prime evaluated somewhere over 2 factorial times x squared. Okay, so now if I look at my alpha n is cosine of 1 over n. Okay, this is 1, so this is my alpha. I can write it like that. This is my alpha. Cosine of 1 over n is my alpha n. And now we can try to figure out how quickly is this thing converging. So we have cosine of 1 over n minus 1. Right? So cosine of 1 over n minus 1 is equal to this error term. So cosine double prime of something divided by 2 times 1 over n squared. All right, I don't know exactly what I'm plugging in here, but the cosine function is bounded, right? Its derivatives are bounded by 1. So this is certainly less than or equal to 1 over 2 n squared. So in this case, if I wanted to approximate 1 by cosine of 1 over n, I'm going to get a rate that's big O of 1 over n squared. And again, the constant here doesn't matter. Okay, and why is the rate important? The rate is important, so I get back to my earlier example, because we want to know how to achieve the desired accuracy. So we need to know how the error behaves so we can do this. So I can say, I'm confident that I have 8 digits correct on my display. Yeah?
So in this case, n would just be 10?
In this case, well, we haven't decided yet what n is going to be in this case.
Oh.
Right? So n is going to be the number of terms we use in our Taylor expansion in this case.
Oh,
right? So that's the question. How many terms in my Taylor expansion do I need to use? I don't want to waste computational time. I don't want to use 100 terms in my Taylor expansion when that's probably way more than I need.
Also, we make use of that.
So we're going to make use of that, exactly. Right? You can try to do overkill and just like, let's use 1,000 terms and we're probably good. But you're wasting computational resources on the one hand. On the other hand, some approximations actually converge very, very slowly. And 1,000 might not get you very close to where you want to be. So these are things to certainly be aware of. All right, so say I want to approximate, let's go back to cosine of 0.1 to an accuracy of, say, 10 to the minus 5. Okay, well, again, I know that if I use n terms in my Taylor series, I can write down the remainder. So the remainder is going to look like, if I use n terms, the remainder is going to look like the next term, the n plus first term. So I'll have cosine n plus first derivative evaluated somewhere. Okay, divided by n plus 1 factorial, and then times 0.1 to the n plus 1. Now, you said we're never going to calculate our error exactly, right? And that's why we've got this unknown thing in here. I have no idea what I'm supposed to plug in for c. But I know that I can put a bound on this n plus first derivative. It's less than or equal to 1. So this is certainly less than or equal to 0.1 to the n plus 1 over n plus 1 factorial. Whatever my error is, it's less than this, right? It might be a lot less than this, or it might actually just be exactly this, but it's less than this. So I know that. I know that my actual error is going to be bounded, and I know that I need to make sure that my actual error is less than 10 to the minus 5. So I'm going to say my actual error is less than this. As long as I can ensure that this is less than 10 to the minus 5, my actual error is going to be even smaller. So this is then what we have to do. We want to choose n so that this quantity here is less than or equal to 10 to the minus 5. Right? If we can guarantee this is less than or equal to 10 to the minus 5, then our actual true error is also less than 10 to the minus 5. And again, it might be a lot less, or it might be really close to 10 to the minus 5. We don't know, but we're guaranteed we have the accuracy that we need. Okay, you're not going to rearrange this and solve for n. What you can do is plug in n equals 1. That just involves multiplication, division. Say, oh, that's too big. Plug in n equals 2. That was too big. If you plug in n equals 3, the result that you get is 4.2 times 10 to the minus 6. And that'll do it. Right? So now I'm absolutely confident that if I do a third order Taylor expansion, my approximation will give me the accuracy that I want. It will give me an error that's less than this, yeah.
So that's the accuracy you want when we have infinite precision, though, right?
That is the accuracy you want when we have infinite precision, absolutely. And then you've got to worry about, sure, if I'm adding and multiplying things, I'm going to lose some significant figures each time, and we just better make sure. And with a Taylor, so with a Taylor approximation like this, each term should be, as long as x is small, like 0.1, each term should be smaller than the term before it by a reasonably significant amount, so that hopefully we're not running into subtracting nearly equal numbers. You could run into the case where all of a sudden each successive term that you're computing is less than 10 to the minus 5, maybe less than the number of digits you could store, and that can happen. So you're effectively adding 0 each time you add a new term on. So things like that can certainly happen. Yeah.
I guess that would be also an argument why not to do overkill.
Yeah, so that's an argument why not to do overkill, is that actually it may not get you anywhere. Okay, you add 1,000 terms, but for the last 900 of them, you had to round to however many digits, 15 decimal places, and it was rounding to 0 every time. So all you were doing is adding 0 900 times, and that's a waste of time. Okay, so if I actually do this, then I'm going to say cosine of 0.1 is approximately equal to 1 minus half 0.1 squared. The third order term is 0 for the cosine series, right? So I stop here. And this now is just, okay, multiplication. Multiplication is not a bad operation. This is small, so I have 1 minus something pretty small. So I'm not subtracting nearly equal numbers. You would only worry if this is on 0.01 or 0.005. So as long as you have enough significant figures to actually store that and store the difference between those, you should be in good shape. And this comes out to 0.995. And if I take this to more decimal places, I get 0.995004165. So indeed I have 5 decimal places correct. And that's what I wanted. My error is sitting over here in the 6th decimal place. And that's fine. That's all we expected. And actually, this bound that we got was actually a pretty good estimate of the error in this case.
So where did the second approximation come from?
So this came from doing the computation with many more terms. Just, again, it's a check. We're claiming that this should be accurate to within 10 to the minus 5. Now this is a simple test case, so we can check and say, is our approximation do what we think it should do? So here I added however many terms, and it looks good. Okay, so we have error coming from approximation of functions. Everything we do is approximation, and you just have to try to do things in ways that are kind of nice and stable. And indeed, if you do this computation and say, I think I need like 5,000 terms to get the accuracy I want, well, now you're going to be worried that, okay, that's fine if you have infinite precision, but in addition to not wanting to do those 5,000 computations, I might not have enough precision to actually store the results of those, because again, I lose significant figures constantly. Yeah.
This would just be the absolute error, right?
That is the absolute error, yeah. Now, if you look at the relative error, that's going to be something on the order of 4 times 10 to the minus 6 divided by something that's pretty close to 1. So you're still going to have a relative error that's less than 10 to the minus 5 as well. What else do we want? We want the method itself to be stable. So we said, I want a problem that's well-conditioned, right? That if I make little perturbations to the data, it produces little perturbations in the solution, not a huge change in the solution. That should be true for the problem we're solving, right? And we saw an example of a linear solve where it was just inherent in the problem. We had these 2 lines that were almost parallel, and it didn't matter how we solved it. This was just kind of inherently ill-conditioned. You could also take a well-conditioned problem and then decide to use a method that is not actually very well-conditioned. So the method will tend to blow up errors, even though the problem itself doesn't inherently do that. Okay, I'll give an example. So this is number 5. We want the method to be stable. Okay, so we have a problem. We know that with the problem, a small change in data leads to a small change in the solution. Now we take this data and we start doing approximations on this data, and those approximations cause errors to accumulate. And now what we don't want is for those errors to accumulate and blow up on us, right? We want it to still be the case after we run through this approximate method that a small change in the data will have led to a small change in the approximate solution that we come up with. So just like the problem, we want small changes in data to imply small changes in the solution or in the approximate solution. Okay, so we know that error accumulates every time we do something. Now what we want to know is how quickly is the error accumulating? Is it just accumulating slowly? Every time I do something, I add another 10 to the minus 15? Or is it kind of accumulating in some sort of exponential way? So how fast does the error accumulate with each step? Okay, so this, we'll do the picture version of it first. So I start with my input data, and my input data is not coming in exact because there's been measurement errors or there's been rounding errors because I have only finite precision or whatever. So there's some initial error in my data before I've done any computations at all. This axis is going to plot error. This axis is going to plot the number of computations. So again, as I do a computation, I expect the error to go up a bit, right? Because I add two numbers together and around. Most likely, that's caused the error to go up. You can get lucky where the error accidentally goes down, but you don't want to depend on luck. So we should expect the error goes up a bit. And what we want is for it to just go up slowly like this. We just add a tiny bit more every time we do a computation. This is about the best that we can reasonably hope for. So this kind of linear growth in the error. Now what we don't want is for this error to start growing exponentially on us, follow this kind of exponential curve, right? Because then after a few computations, our error might be really getting out of hand. So exponential growth in the error is what we want to avoid. Slow linear growth, we're happy. That's the best we can do. Exponential kind of curve to the change in error, that's bad, right? That means before long we've got some useless number in our hands. So for linear growth, we're going to say that the error after n computations is linear, so wherever our starting error was, plus something that's linear in the number of computations. Okay? And here C is a constant. Okay, so this is good. If we get in this situation, we say, okay, this is an acceptable growth of error that we can live with because we can't really do better than this. Okay, exponential growth in error is going to look like this. When we have exponential growth, okay, now we have something that's exponential in the number of computations. We're going to have our initial error times some constant to the nth power. And if our constant is bigger than 1, we're going to get this shape, this exponential growth. Okay, this is unacceptable. So if you analyze your method and you say, oh, it's going to do this to the error, then that's not the method that you want to use. So I'm going to do an example of this. So I'm going to warn you now, this example is going to feel to you really contrived. It's actually the exact kind of computations, the exact kind of analysis we're going to see when we get to solving ODEs, initial value problems. This is identical to the analysis we're going to do for initial value problems. Yeah. Yeah, so I mean, if C was less than 1, then this would cause the error to go to 0. And if the error goes to 0, then that's great, right? When I see papers where they claim things like this with C less than 1, then I'm pretty sure there's a mistake in the paper, because your methods don't typically do that. Okay, so let's consider we've got a little recurrence relation here. Again, this is how we're going to actually solve ODEs in a few weeks. So let's consider this recurrence formula. Okay, for computing this result, Pn equals 1/3, 1/2 to the n. This isn't the recurrence formula. This is the thing we actually want to compute. Okay, so we might be interested in the result after n steps of this, for example. And then it's just some number that we're trying to compute, but we have a method to approximate it. Okay, here's the recurrence formula. Recurrence formula is Pn equals, okay, I take 5/2 of my previous value, and I subtract off the value before that. And now, obviously, to kick this off, I need two values to kick this off. So I'm going to give you a couple of values. I'll give you P0 is equal to 1/3, and P1 is equal to 1/6. Okay, you can check these values work. So with n equals 0, I get 1/3. With n equals 1, I get 1/6. So these initial values work. You can plug this in here and simplify fairly easily, and you can check that indeed this is a solution of this recurrence relation. So I'll leave you, you can believe me for now and check on your own time. But that's a simple check. But now let's see what happens when we actually use this recurrence relation in practice. And we're going to use it not with infinite precision, but with finite precision. So I'm going to have a table here. I'm going to have the results when I do 5-digit computations. I'm going to have the results where I do exact computations. So exact. I'm going to do exact, and then once I've done the exact for however many steps, then I round to 5 digits. At that point, I can be sure I actually have 5 digits accurate. Okay, and we're going to look at the relative error. Okay, so P0, P1 are given to me. I do a computation, and I compute P2. So with 5-digit arithmetic, again, every time I add or subtract or multiply or divide, I round to 5 digits. And for P2, I get 0.083350. Okay, the actual answer is 0.083333. So in one step of this method, what have I done? I've produced a relative error that's around 2 times 10 to the minus 4, something on the order of 10 to the minus 4. Okay, 5-digit arithmetic. If each step of my method requires a few steps, and each step adds another error of 10 to the minus 4, that's probably reasonable. So now what I'd like to see as I go down this table is that I get in the next line something like 4 times 10 to the minus 4, 6 times 10 to the minus 4, 8 times 10 to the minus 4. That would be linear growth. That would be great. Okay, what am I actually going to say? Well, I'll take us a few lines down. So what would I like to see down here? Maybe something on the order of 10 to the minus 3 would be reasonable at this point after 10 steps. All right, what am I actually going to see? I do the computations with 5 digits. Get 0.0067360. That's my 5-digit number. Okay, my real number is 0.00032552. Those don't look the same, actually. The number of leading zeros here is actually different, right? So what's my relative error? My relative error is something like 20 at this point. 20, I was hoping for 10 to the minus 3. 20 is not 10 to the minus 3, right? Something's gone very wrong here. if we plot the error, we're going to see exactly this picture, an exponential growth in the error. So this is clearly unstable, right? In 10 steps, or less than 10 steps, my error has gone up by something on the order of, what, 10 to the 5th or something, right? That's kind of bad. So let's try to figure out why. Again, we want to not look at these situations after the fact and say, you know, this isn't even the case where this number blew up on us, right? It's still some number. It's not coming to numerical infinity. So if all I had were these numbers, I wouldn't look at these necessarily and say, oh, that's obviously wrong. Which means I need to be able to know ahead of time this was going to happen. I need to be able to look at my method ahead of time, analyze it, and say, this method is unstable, don't trust it, or this method is stable, it's going to grow errors in this linear way, and we believe that this, so we can trust the results we get out of here. We can trust that the error is not going to blow up. We need to know that. So how do we analyze this? What happened? Well, the problem started really in this step. When I used my method, I didn't use 1/3 as my initial condition. I used 0.33333 as my initial condition, right? Because all I've got is 5 digits. And that's where the whole problem started, before I even did these computations. These computations took that and made it a lot worse. But they started by working with something that was accurate to 5 digits, the best that I could hope for. So we started with this small error in our inputs. So we used, instead of P0, we used P0 tilde, 0.33333, and we used P1 tilde, not to be 1/6, but to be 0.16667. Okay, small errors, right? Those are the size of errors that we know we've got to deal with when we're working with 5-digit arithmetic. Somehow our scheme took these errors and just blew them up. So let's go back to our scheme and see what's going on. Why is this scheme somehow ill-conditioned? It's taking a tiny change in the data and leading to a very large change in the final output. Okay, so here's our scheme. Pn equals 5/2 Pn minus 1 minus Pn minus 2. Okay, and now I'm not even actually going to worry too much right now about the fact that we're running this scheme with 5-digit arithmetic. I'm just going to see what this scheme does to these errors. What we're going to do is look for solutions of this scheme. What do the solutions of this scheme really look like? So, and this, again, when we start analyzing methods for initial value problems, this is exactly what we're going to be doing. We're going to look for solutions of this form. Okay, so Pn is equal to beta to the nth power. Okay, so I plug that in here. I get beta n equals 5/2 beta n minus 1 minus beta n minus 2. Okay, for various values of n. So you might be worried that we're solving basically an nth order equation for beta, but we're not really, because I can factor out a lot of these betas. It's actually really a quadratic equation, exactly. So what do I have here? If I factor out a beta n minus 2, I get a beta squared minus 5/2 beta plus 1 is equal to 0. Okay, so the solutions of this are either beta equals 0 over here, which is a trivial solution, or solutions of this quadratic equation, which are 1/2, and 2. Okay, that means 1/2 to the nth power is the solution of this. 2 to the n is the solution of this. And since this is linear in the piece, I can take any linear combination of these and get new solutions to this recurrence relation. Right? So that's the key. I can come up with actually the general solution to this recurrence relation.
That equation where there is like a kind of characteristic equation would be compared to solving ODE.
Yeah, so you will, exactly, you will have seen this when you solved ODEs. If you took just like an intro ODEs class, you will have done things like this. Okay, so here's the general solution to the recurrence relation. Okay, Pn equals some constant times 1/2 to the n plus some constant times 2 to the n. Okay, and how do we determine the constants? We have two unknown constants. Well, they come from our two initial conditions, right? We know P0, we know P1. So by requiring ourselves to get the right values of P0 and P1, we can figure out what C1 and C2 should be. Okay, so if we're given the exact P0 and the exact P1, we get this. C1 equals 1/3, C2 equals 0. Okay, so Pn is equal to 1/3 times 1/2 to the n. And that makes sense. That was actually the exact thing we were trying to compute. So we'll sanity check here. This works. Now, of course, we didn't compute with these values. We took them and we rounded them to 5 digits. So what happens when we are given instead these approximations? They're pretty good approximations. P1 tilde was 0.16667. Okay, so nothing horrible happens with the C's in this part of the computation. I get C1 tilde, which is 0.33333. That's about as good as I could have hoped for. And I get C2 tilde equals 2.5 times 10 to the minus 6. So again, given that I'm working with 5-digit accuracy, this is a really good approximation to 0, right? That's about as the best we could hope for. It's better than 10 to the minus 5. Okay, but what does that mean we actually computed? Yes? Okay, it depends how you're doing your 5-digit arithmetic, but typically you would count 5 significant figures, and then you would keep track of this exponent here. Now, if you try to add these two things together, now you will have lost this. But 5-digit arithmetic would be able to store this number typically. So that's the crux of it. This is tiny. This is close to 0, which is great. The problem is it's multiplying 2 to the n. It's multiplying tiny times something that gets big really, really quickly. So what we actually computed is P tilde n equals 0.33333 times 1/2 to the n, no big deal there, plus 2.5 times 10 to the minus 6 times 2 to the n, and this is where our problem comes in, right? We've got this 2 to the n, and even though it's multiplied by something small, 2 to the n can get bigger than 10 to the minus 6 over small values of n, right? It didn't take long. So this was our exponential term. And again, this is what we're going to do when we start analyzing methods for initial value problems. We'll do this kind of analysis we'll look at the betas we get, and if the betas are less than 1, we'll say, okay, great, that's stable, right? This is going to go to 0 as n gets large. If the betas are bigger than 1, we're going to say, hold on, that's a problem. This is going to take any tiny error in this coefficient in the input data that we have, and it's going to blow it up in a hurry. So if we analyze our method and get something like this, we're going to say, no, don't use this method, right? We can't trust it. Right? And we could do that analysis without actually knowing what the exact solution is, right? All I needed to know was these betas.
Once we conclude that that method, that approach is no good, so
Yes.
how do we fix it? And
Well, so once we conclude this approach is no good, how do we fix it? So, I mean, we will talk about this when we get to the methods on initial value problems. We're going to see a lot of methods like this. The short answer is you say that method is no good, we need a different method. And we're going to see lots of different ways of building these kind of methods. And some are good and some are not. But the analysis is important, yeah. Right. Any approximation we make to this number will have an error in it, and it's an uncontrollable error. So any method that does this, we're going to call the method unstable, yeah.
Each method usually cycling back and forth to find an appropriate method that's going to realize the solution.
So are we cycling back and forth? How do you mean?
So when you said that if you have, when we go back to identify one method
Yeah.
and then approach to get a solution, then you say that we select another one.
Yeah, so we'll have to, so if we get if we say, I'd like to try this method, and we do this analysis and get something like this, we're going to say, throw that method away. That's no good. We'll go back and say, we need to do something different. We need to find a better method, yeah. And, I mean, doing a mathematics is a process of trial and error a lot of the time. We have all these nice textbook results and clean proofs, of course. Nobody ever wrote the proof that way, or the method that way on the first try, right? They threw away a huge stack of wrong results, yeah.
Theoretically, will we finish our analysis the second we know that general solution was other than the exponential, or was it really dependent on the fact that we were given initial conditions that couldn't cancel?
So what's the when are we finished the analysis?
I'm saying we went through the whole thing and we found that we had an exponential term, and
Yeah.
even though we had a very small initial condition
Right.
that looks very close, it wasn't. Was it theoretically
So-
possible that we could have found one that
So
would
no,
have
so the
canceled?
initial conditions weren't really where we finished our analysis. We really finished our analysis right here. As soon as I said beta is 2 and that's bigger than 1, we said, oh, we're done. That's going to blow up on us. We knew we were looking for solutions of this form. 2 to the n, and we said, no good. That's going to blow up any small error. Okay, we could get really lucky, right? But you never want to count on luck. Yeah.
Whenever we have a critical recursive sequence, you analyze it using the exponential as a solution.
Typically, when we're doing this kind of linear recurrence relations, we'll look for these exponential terms as a solution, exactly. And the fact that this was a 2-step recurrence relation meant that we were basically solving a quadratic at the end of the day. If it's an n-step recurrence relation, we'll solve an nth order polynomial. It's exactly the same as when you're doing ODEs. And so, I mean, that's kind of nice. That's kind of what you like in a method when you say, the original equation has this kind of structure or flavor to it, and now I build a method, and the method has really the same kind of structure, flavor to it, and that's good. I think that's something that you like. Yeah.
So you mentioned how, because we have this 2 to the n term, this method blows up,
Yep.
it's knowledge. It's not even, the fact that in the case of 1/3 or 1/6 exactly, if you're doing exactly, the 2 to the n term goes away, would even that scenario be considered an invalid
So we'll
or unstable? Or?
just say I had the case where the C2 tilde I came up with was also 0, right? Which could happen, right? Okay, then yeah, the method is going to behave itself for that case. We're still going to call it an unstable method because, again, if we happen to make any little change in our initial data, right, that safety factor goes away. Right? So yes, you can get lucky. You can have an unstable method and you can pick just the right initial conditions where it actually gives you the result that you want. But the issue with the unstable method is that not what it does for any one particular value, but it's that small changes in your input can lead to massive changes in your output. Yeah.
So I'm asking, is another way to kind of think of it, do we basically need to check whether a piece of n basically converges Does it yield stability, or is that different?
Yeah, so we need to check whether p to the n converges. Yeah, so what we're going to ask for actually is that these p to the n's converge to 0. So again, we'll see this more when we get to the actual ODEs. What we're essentially doing is saying, let's take our method. Let's see what it does on a simple class of ODEs where we actually can write down the exact solution very easily. And in this class of ODEs still have solutions that go to 0. And let's make sure, let's do a little sanity check here and make sure that this works on the simple ODEs where we can actually check for sure what we know is supposed to happen and make sure that that really does happen. Okay, so stability. Stability is a big one. Then another thing that you might care about is just how long does your method actually take to run? So if you're doing an iterative method, an example of an iterative method would be Newton's method, right? Where you say, I'm trying to find the root of an equation. So I start with an initial guess, all right? I plug it into some formula that involves f and the derivative of f, and I get a new result out. I take that, I plug it back into the same formula, and I get a new result over and over again. And the idea is that the more steps of this you do, hopefully the closer you get to the root of the problem, right? The thing you're trying to solve. So then the question is, well, how many steps do I really need in order to get the accuracy I want? How many iterations do I need?
That's like time complexity for the.
Yeah, so we're thinking about sort of time complexity, absolutely. Do you have a method that, okay, it converges, but you need to take millions upon millions of steps? Or do you have a method where, a handful of iterations and you're done? You've got an accurate enough result. So these are other things we care about because throughout this last class, most of the time, we're not given a problem and say, do the computations and get back to me in 20 years with the result, right? We want the answer now. Time is money, literally when you're buying time on a supercomputer, right? So we want methods that ideally work quickly. This pen's on its way out. So for iterative methods, we want our error to decrease quickly. Okay, so iterative methods were basically sequentially computing a sequence. Okay, p to the n. Or again, p to the n might be the result of Newton's method after n iterations. And we know as n goes to infinity, it's supposed to converge to the value that we really care about. But we don't have time to do infinitely many iterations of this. We've got to stop at some point. We need to know when to stop. And we hope it's not 20 years from now. If it is, then we maybe want a different method. So, okay, quickly is kind of a relative term. But let's try to get a handle on what we mean by fast convergence. So what I mean by fast convergence, I guess, is every time I do a new iteration, I get a substantial improvement in my result. So I had some error after n steps. I do take an iteration, and my error went down quite a bit. That's what I would like. Every time I do an iteration, my error goes down not just a teeny tiny little bit, but hopefully quite a lot. So the error, we're going to say we want the error after n plus 1 steps to be much less than the error after n steps. Is that a reasonable definition of fast convergence? I mean, it's still a hand-waving definition, but that seems reasonable. Okay, or in other words, I want Pn plus 1 minus p, this is my error after n plus 1 steps, should be much less than my error after n steps. Now, slow convergence would be if the error doesn't really change much after each step. You know, maybe I'm trying to compute the number 10 or whatever. Every time I do an iteration, the error goes down by something like 10 to the minus 10. Okay, the error is going down. We'll eventually get there, but it's going to take a while. We're not so happy with that. So by slow convergence, that's what I'm going to mean. That the error after n plus 1 steps, so Pn plus 1 minus p, is not really that much different than the error after n steps. You know, it's probably smaller, but it might not be much smaller. Okay, so let's try to give some definitions that are a little less hand-wavy than this. These and these right now are kind of, they mean whatever you want them to mean. So let's try to make this precise. Let's suppose, again, that we have a sequence that converges to something. Okay, and we're going to suppose that that's never actually equal to the result. Right? It gets closer and closer, arbitrarily close, but never actually hits the exact solution. Now, we're going to introduce some constants. So if there exist some numbers, lambda and alpha, that are greater than 0, such that the limit as n goes to infinity of, okay, and again, we're going to be comparing our new error to our old error. So the way we're going to do that is look at Pn plus 1 minus p divided by Pn minus p, but we're going to raise it to the alpha power. And we're going to say this is limit is equal to some value, some number, lambda. Then we say that Pn has order alpha convergence. Okay, with error constant lambda. So there are some special cases. One special case would be if alpha is equal to 1. So what's that?
Linearly
That would be linearly convergent, exactly. So if alpha equals 1, we get what's called linear convergence. Okay, and what does that mean? That means as n gets larger, we're going to have Pn plus 1 minus p approximately equal to lambda Pn minus p. Right? And hopefully lambda is less than 1. If lambda is bigger than 1, then we're not getting convergence at all, for this case of linear convergence. Okay, so what does that mean? It means the error is not changing that much, right? It's the error after the next step is still really proportional to the error from the previous step. We haven't really gained significant figures or anything. Yeah.
Does that mean converges like all of n in that case, or is it different?
So it doesn't. It's not quite the same as being O of n.
Oh.
So.
I mean, for the linear case.
Right. So O of n would have more to do with, I guess, the size of these terms.
The size of it.
So this is what we're going to call slow convergence. All right. Linear convergence will get us there. Okay. There's always a trade-off. Methods that are linearly convergent tend to be more stable. Methods that have faster convergence you can also run into issues of stability, or you need a really good initial guess. So there's always trade-offs. So just because you said, this method has order 4 convergence, doesn't mean it's a great method, because there could be problems with stability. I could need an extraordinarily accurate initial guess. It could be extraordinarily complicated to run. So there's certainly trade-offs, but we're not that happy when we're stuck with a linear method. Sometimes we are. Sometimes there's no way around it, but you don't want to be stuck here longer than you have to be. Now, if alpha equals 2, this we call quadratic convergence. And this means that the new error is going to be proportional to the old error squared. Right? So that means if we started with an initial guess that was reasonable, right? Now we effectively square the error. So maybe we started with 0.1. Now our new error is 0.01, right? 10 to the minus 2. Then we square it again, and after the next step, we have error like 10 to the minus 4. We're basically doubling the number of significant figures with each step. And that's good. That means each step is actually giving us a substantial improvement on our accuracy. So this we'll call fast convergence. And this is what Newton's method does, and we'll see that in a little bit.
Professor,
Yeah.
isn't there another type of convergence that is not quadratic, but it's kind of linear, but we call it superlinear convergence?
Yeah, so this is not the only possibilities. These are the most common possibilities that you'll see. But you can certainly have other values of alpha. And yeah, if alpha is bigger than 1, we'll call that superlinear convergence. And that's good. Quadratic is great. Superlinear is certainly much better than linear. And we'll see as we get to other methods and do some of this analysis, we'll see other values besides 1 and 2 pop up. Yeah.
And this only applies to like iterative.
This applies to iterative methods,
So like
exactly.
Euler's method and stuff like that, for example.
So let's see, Euler's method, it depends what you're doing with Euler's method. So if you're trying to solve an initial value problem in time, that analysis would look a little more like the recurrence relations that we just did. Okay. So then say I want to know, I start at time 0 and I want to get to time 1, right? Well, after 4 steps I've got to time 1. I'm not going to do better by letting n go larger and larger. Now I'm just getting past time 1, right? And sometimes you're using Euler's method to solve something to steady state. And then you really do want to let n get larger and let time go to infinity. In that case, you would view that as an iterative method, yes. Any other questions on this? Yeah.
Does the method always have just one rate of convergence, or can it shift?
Does the method always have just one rate of convergence, or can it change? So I'll say what we care about is what happens in the limit. So whenever we're talking about these kinds of rates of convergence, order of convergence, you kind of don't care what happens when n equals 1 or when n equals 5 or things like that. So you may have it doing very slow things initially. Or like for something with Newton's method, you need a good initial guess. So if you start with a large error, you just might not get convergence at all. Or you might have to do extra tricks to it to try to force yourself there that will slow it down. So typically with this, we care about this limit, what happens eventually. Similar to the picture I drew before of the errors under this curve, where I said, okay, initially they could be above the curve. As long as they're eventually underneath the curve, then we can use this big O notation. Other questions? Less things to worry about for errors. And to know that we actually don't have to worry too much. Like we have ways of analyzing errors, right? And so that we can have some confidence in our methods. So moving on to next time, we're going to start root finding problems and start trying to actually build some numerical methods for useful problems.